Good morning, friends. I feel immense pleasure to be here again for my course, Flight Mechanics. In the Flight Mechanics, I am in module number 2, that is cruise flight. Before this cruise flight, I have already covered about atmosphere, different types of layers of atmosphere, thrust required, power required, velocity, lift, drag polar, and so on. I have already covered. Today I am going to take the very important topic for the flight mechanics, that is a very important phenomena for aircraft performance, that is range, and range for jet powered airplane. That is I am going to take in today's lecture. So, as you know, my name is Dr. Yagya Dutta Dwivedhi. I am professor from Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad, India. And my today's lecture overviews are range for jet powered airplane, types of range, different velocities, constant altitude range equation, cruise climb, constant velocity cruise. So this I am going to take, and after that I will try to cover up the range for propeller aircraft. So what is the range? This I am going to discuss today. So range is a distance. So what is the range? Range is the distance covered by any airplane with given amount of full tank of fuel. So this is the basic definition, and our objective is to have maximum range. So range means it is distance from here to here, from A to the B, and from here to here how much distance in nautical miles or in kilometers it is covering. So that is the range for any of the aircraft. This we are going to take today, and in the different format, different types we are going to take today. So now we have already seen the range, but if we talk about the endurance, and what is endurance? Endurance is the time or maximum time covered by any airplane with given amount of full fuel of tank. So these are the, so here it is a distance and here is the time. Endurance related to the time, how much time it is loitering. If aircraft is flying like this, how much time it can afloat in a given amount of fuel. When the tank is full, and by that full amount of tank, full fuel in the tank, how much time it is airborne. That is the endurance. So we will see that how the range is related and how the endurance is related and how these things are happening for the jet powered aircraft. Now we will see that change in the weight, because as the aircraft is flying, fuel is consumed. So the rate of change of the weight of the aircraft, that is dW by dt, is always negative, and this is here Ct. T stands for the thrust producing engine. It is a specific fuel consumption for the thrust specific fuel consumption. T is here thrust, G is the gravity. So we can write it as a dt is equal to minus 1 by, okay, this you can see here. So if you want dt here, so this will go up and this will go down. So it is a minus 1 by Ct into T, capital T, into G into dw. So this we have mentioned here. So now we can do some changing. You know that T is equal to T, and we can write W by L because L is equal to W. So it is L by L, but this W by L we can write T as a thrust, this thrust as a drag, and this is the W. So here we can write it as a W weight CD by CL. So here one more term I can write here, this T is equal to D. I can write here D into W by L. I can take out W outside, D by L, or W into CD by CL. Also I can write CL. I can write W by CL by CD. So this is the your thrust is equal to, for the T we can write W by CL by CD. This transformation we will use here. For T we will write here, this we will replace here. So here dt is equal to minus 1 by Ct. This is wrongly here mentioned here. Here we can write CL by CD into 1 by W into dW. So here in place of T, W by CL by CD. So this CL by CD will go up. So here CL by CD into 1 by W into W, because we want to integrate with respect to the change of weight. So here limits are given here that at T0 weight is W0, means it is a full weight at the time T0, but at the end T1 the weight is W1. So endurance is equal to difference in time T1 minus T0 is equal to here integration of dt with respect to T0 by 2 T1. So we can write this as the endurance here, left side. So this endurance E is equal to minus 1 by Ct into G, CL by CD, W0 to W1, 1 by W into W. So this we have got one equation, and now if we integrate this, we will get here E is equal to minus 1 by Ct into G, CL by CD, and 1 by W is equal to ln natural log W1 minus ln W naught. So W1 by W2. If we reverse this limits, so this sign will go. So now 1 by Ct into G, CL by CD, ln W naught by W1. Minus sign has gone because W, these limits are changed here. Here it is the from W1 and here W naught. So we have got this value. Now here if you see, this equation is the endurance equation, but there is a very important physics behind this. Your endurance is combination of all the stream of aeronautics, that is your Ct is a specific fuel consumption. It is related to the propulsion of the aircraft. CL by CD is your aerodynamic property, and your W naught by W1 is your structural property. So here we have how much fuel is consumed. So it is a fuel consumption here, and so fuel consumption. So maximum E, to have this E maximum, your CL by CD should be maximum. That is the important of this thing. So there is a minimum drag speed, and this minimum drag speed, for the minimum drag speed, we write as a V minimum drag or MD is equal to CL is equal to under root CD naught by K, and we have seen that the CD naught plus KCL square, and we have that this CD naught is equal to half rho v square s CD, okay, and here 1 by it is w square by this thing. So this is your, here is A, and here this is equal to B. So here V minimum drag is equal to B by A. This divided by this 1 by 4. So this is the condition for the minimum drag. Okay, so in this way we can find out the endurance, and if you want the maximum endurance, we should fly at a minimum drag, and this minimum drag velocity we can find out from here by this way. So now we will see the types of range of the aircraft. So now we have the first one is the safe range. So what is the safe range here? This is the SA, safe range. So it is the maximum possible distance between two airfields, including takeoff, climb, cruise, descent, landing, and includes all fuel reserves. So if it is here, it is parked on the dispersal. From here it is takeoff. This is the takeoff. Here the climb. From here cruise to descent, loiter, again descent, and this landing. All these things, this is the cruise here, this is the climb, this is the descent, this is the loiter, and this is the landing. All these things, how much fuel it is consuming, how much range it can cover by the given amount of fuel is called the safe range. Next one is, this is the first one. This is the second one is still air range. It is also told as a SAR. So this still air range, when aircraft take off, climb, and then cruise at altitude until all fuel is expended in mid-air. So it is in this landing is not up to here. This is your still air range. It is called still air range. So this is it is not landing and descent is not there in this. Up to runway, it is taking off, climb, cruise. So how much distance it can go in the cruise by the given amount of fuel, that is called the still air range. Third one is the gross, that is GSAR, gross still air range. It is called GSAR. Aircraft starts cruise at a given altitude and continuously it is all the fuel is expended. So here this is not there. This, so up to here this is the climb, but from here it will start. In cruise, how much distance it is covering in the cruise, that is called the GSAR. In this one, this is not considered. So this type of flight or this type of range, which is calculated from the cruise, and during this cruise the fuel is consumed, that is called in mid-air itself, that is called the gross still air range. Now we will calculate the range. We will derive the range of the jet powered airplane. It's very important that we have to understand that this range is a distance, and we know this distance is equal to, if you see, V is equal to S by T. So this range is equal to S. So S is equal to range. I am writing range is equal to V into T, and T is your endurance, time. So here we have mentioned that range is equal to time into velocity or endurance into velocity. If this velocity is 0, which it is not acceleration, it is unaccelerated flight, so dv by dt is equal to 0 or the constant. So we can get that this ds, we can write that ds is equal to, we know E is equal to minus V, E is equal to minus 1 by Ct into G, Cl by Ct, 1 by W into dW. And here is the velocity, so we have mentioned here this velocity, but we know that this velocity we can find out from, for the cruise, we know that L is equal to W is equal to half rho V square S Cl. So V is equal to under root 2 W by S rho Cl. So this value we will put here, and then we will see how we are going to derive this equation. So now this ds is a small change in distance. This ds is equal to minus 1 by Ct into G. For this V we will put under root 2W by rho S Cl. This is the S here. 2W by rho S Cl. Here we have the Cl by Cd, and here we will see that 1 by W into dW. So now we will make some simplicity in this. Minus 1 by Ct into G. Here 2W by rho S. This Cl if I take outside, so here you will get, here is a Cl to the power, just Cl divided by Cl to power 1 by 2. So what we will get? Here we will get Cl to power 1 by 2. So 1 minus 1 by 2. So you will get, so here I am putting Cl to power 1 by 2 by Cd, 1 by W into W. For maximum range, so we got here this ds, and this is called the range also. So this maximum range, Cl to the power 1 by 2 by Cd should be maximum. So this is the condition for the maximum range, that Cl to the power 1 by 2 by Cd should be maximum. Here we get, we have to understand different velocities. So here we get V is equal to 2W by rho S, and for the Cl, for maximum this thing, we should have under root Cd naught by K. So V for a minimum drag, we should have the 1 by 1.32 into V into minimum drag. So here maximum jet range is at a higher speed. So it is at the higher speed. So we know that Cl is equal to under root Cd naught by 3K. So V for the maximum range is equal to 2W by rho S, Cd naught by 3K. So here we will get under root 3 here, we will get V mid, minimum drag. So it is 1.32 of the, for the, so it is very good result is coming that for the maximum range velocity, what is the velocity at which we should fly? The velocity is 1.32 times V minimum drag. Means it is 32% higher than the minimum drag. If you fly, your range will be maximum. So maximum range speed is 1.32 times of the minimum drag speed. So we have to give this condition. So we will see here. So now we have different types of ranges. First one is the, we have a simple case we have already derived. Now we will have the constant altitude and the constant velocity. We will see that. So constant altitude cruise range, in this your altitude, this density will remain constant. So you can say that constant density cruise range. So we need to integrate this equation as W naught is extending to W1 and this L naught is expanding to L1. So we can write here that Cl is equal to 2W by rho SV square. Now here we will put for this Cl, we know that under root Cd naught by 3K. So here W getting smaller and smaller. So as you increase this value, your W will be small. So this W by V square is equal to constant, or it is a constant aircraft velocity. So here we can say that W by rho is equal to constant. So W by rho is a constant here. So V cruise climb. So we can see that constant altitude rho cruise. So here we can see that ds is equal to minus 1 by CTG under root 2 W by rho s, CL to the power 1 by 2 by CD, 1 by D into dW, minus 1 by CTG. Here we can see that we can take out, because this W will be here. It is not constant now. So under root 2 by rho s, CL to the power 1 by 2 by CD, 1 by W to the power 1 by 2 dW. So now we have to integrate this equation from S0 to ST. ds is equal to minus 1 by CT G under root 2 by rho s, CL to the power 1 by 2 by CD, from W0 to W1, 1 by W to the power 1 by 2 into dW. So this is here the range. We can write as a R. This R is equal to minus 1 by CT G under root 2 by rho s, CL to the power 1 by 2 by CD. Here we can write it 2 W1 to the power 1 by 2 minus 2 W0 to the power 1 by 2. So if I take this 2 common and if you enter here, so it will become 4. 4 into 2, it will be under root 8. So R is equal to 1 by CT into G, and here if you change from here to here, W okay, like this, W0 to W1, this sign will be removed. So here we will get R is equal to 1 by CT into G under root 8 by rho s, W to the power 1 by 2 CD, W0 to power 1 by 2 minus W1 to the power 1 by 2. So this is the range equation at constant altitude flight. So we have different types of flight. If you remain your aircraft at a same height, you have to use how much range? Range will come as per this equation. So here we have the relationship between CL and the CD. So CL is equal to under root CD naught by 3K. We can write CD is equal to CD naught plus KCL square. So here the CL square is equal to 3 CD naught. So here total CD will be 4 CD naught. So for this condition, your CD should be 4 times of the zero lift drag. This is the one more condition we have got it. For this condition, your CD should be 4 CD naught. Total CD. CD is a total coefficient of drag. So this is this much. So now we will discuss about the fuel burn. What is the fuel burn and how much we are observing this fuel burn. So fuel burns, aircraft get lighter, change of weight is integrated, rate of weight reduction is depend on the fuel. So here we can see this CT is equal to thrust specific fuel consumption, and if we write only C is a specific fuel consumption, the units of this thrust specific fuel consumption is kg per Newton second, gram per kilo Newton second, or kg by kg Newton second. This is a unit, but here it is a kg per watt second. That is the difference. So we have to be very careful. We are using this one for the propeller aircraft, and this one we are using for the jet aircraft. So this unit is a little difference here that we have to take very much care of. Now the next condition or the next flight cruise is called the cruise climb or a constant velocity cruise. So we have seen the constant altitude or the constant density. We have already derived the equation. Now here constant velocity cruise. So here we will see that ds is equal to minus 1 by ct into g under root 2w by rho s cl to the power 1 by 2 by cd 1 by w into dw. So at sea level, at the ground, we have the weight of the aircraft is w naught and the density is rho naught. So w naught by rho naught is a constant in this case. Means the w by rho is constant. So here if you see this w itself is a constant, we cannot make this thing here. That is the difference. So here we will see that minus 1 by ct into g 2 w naught by rho naught s here cl to the power 1 by 2 by cd ln w1 by w naught, or we can write that this range is equal to 1 by ct into g 2 w naught by rho s cl to the power 1 by 2 by cd ln w naught by w1. If we reverse this, this minus will go off. So we got this another equation, that is the range equation for a constant velocity cruise. Here if you see constant speed cruise range, it is called the constant speed cruise range. If the pilot is maintaining a constant speed, how much it will go? So this you can calculate from here, and it is under root 1 by ct into g. G is a acceleration due to gravity. 2 w naught by rho naught into s is area. Cl to the power 1 by 2 by cd natural log w naught by w1. And here also for the better range, as at high altitude your cd naught should be 4, cd is equal to 4 cd naught. This is the drag condition. Your cd should not be more than this. If it is this much, then only you will go for a long distance. Now we will discuss, as of now we have discussed the range for the jet engine. Now we will try to discuss the range for the propeller aircraft. There is a little difference. You know that I have discussed just now that there is a change here. This is for the propeller. We are using the specific fuel consumption, and here we are using the T. It is a thrust specific fuel consumption. That is, we have to take very much care. Unit is also different. So you will see here that the rate of change of the fuel consumption, that is dw by dt, is equal to minus c into p into g. There we used to have the T. Here we have the power, not the thrust. So for propeller aircraft, we have to use the power. So here this power is not equal to dv. Power is equal to not, here if it is a d, it is a thrust. But here it is not equal, because this p is equal to dv by eta. Eta is a efficiency. So this is the propulsive efficiency, and it is always less than 1. So this p will be always more than the dv. That we have to understand, and this is happening due to the heat, noise, friction, and so many other parameters which makes this efficiency less than 1. So here we can write here that dw by dt is equal to minus c into g, and for this p we can write dv by eta. So dt is equal to, because first we have to find out the time, that is endurance. Dt is equal to minus eta by c into g into dv into w. So this dt is equal to minus eta c g into v. Here we can write for this d, we can write the cl by cd. Here we can write 1 by w. This you can see here. D is equal to D into W by L. So W we have taken out. So here it is D by L. So CD by CL. So this CD by CL we have put here below this, and this has become the D. We can write CL by CD by W. So here 1 by W into dW. So here endurance is equal to eta C into G into V CL by CD ln W naught by W1. So this is the endurance equation. Endurance equation for propeller aircraft. Please take care that there is a difference between a propeller and the jet aircraft. So here E is equal to eta is efficiency, C is a specific fuel consumption, G is a gravity, V is a velocity, CL is a coefficient of lift, CD is equal to coefficient of drag. It is natural log. W naught, it is total weight divided by empty weight. This gives the difference of the fuel consumption. So endurance, for maximum endurance, your CL by CD should be, this should be max. And this should be minimum. This should be minimum. Velocity should be minimum. And this should be maximum. Means fuel storage capacity, if it is maximum, you will have highest maximum range, maximum endurance. So this we got now endurance. Now as we have seen in the jet aircraft, we know that we have to find out the range. And this range is equal to E into V. Same equations we will be using. So here this V is equal to under root 2W by rho S CL, and this is to maximize the V. So this CL by V into CD. So we can write that L by V into D, and this V into D is equal to power. So it is L by P. So for a minimum power speed V is inversely proportional to 1 by PR. Here P is equal to power required. Okay. So this, as you, if you go high speed or if you have the high power, your velocity has to be less. So this relation we have to take care of. For the minimum power speed, V is inversely proportional to the power required. So if you see here, like this, so this V. So as the power is increasing, the velocity will also, it will decrease. So now we will discuss about the range of the propeller power airplane, and we know that R is equal to neta by CG CL by CD ln W by W1. So here also the CL by CD is maximum, and this, the velocity is equal to B by A to the power 1 by 4. Range is not the function of the altitude rho. So here if you see, there is no rho. Rho is not there, and this E is equal to neta by CG under root rho S CL by 2W CL by CD ln W naught by W1. So in this we can see that we will be discussing about these topics. These are the references which I have taken from Anderson JD, Aircraft Performance and Design, International Edition, McGraw-Hill's first edition, 1999. Isel by ME, Aircraft Performance Theory and the Practice, AIAA Education Series, AIAA 2. Any questions you are welcome to ask. I also like and subscribe this channel. Any questions you can communicate to the chat box, or you can send to my Yagya Dwivedhi @gmail.com. So thank you very much. Please do wait for my next lecture on the flight mechanics. Till then, goodbye. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.